Hello everyone, thanks for joining. So we'll start by 6:10. Now it's 6:03. We'll wait for a couple of students to join and then later from 6:10 we can start. So I guess hello. Still. Hello. Okay, am I audible? Uh, can someone please let me know if am I audible to you?
Yes, ma'am, you are audible.
Yes, ma'am.
Thank you. So I don't know why this echo thing was going on. Okay. So, hello all. This is fourth week. I'm your TA Jagriti Patil for the course Data Analytics with Python that is taken by Professor A. Ramesh from IIT Roorkee. So, I'm a third year PhD fellow at IIT Gandhinagar in the Department of Biological Sciences and Engineering. This is likely my second year doing this NPTEL TA duty, and my research lies in the field of ultrasound. So I do some mathematical modeling for tissue characterization in order to see if we can help clinicians for better as well as early diagnosis. So that was all about me. We'll start with the week. So week 4, and it's like the lectures which were done in week 4. Also, with respect to it, we'll also do some couple of things from week 3 that was about confidence interval, and later we'll do for the week 4 also. So today we also have a little bit of numericals that so I thought, okay, switching it to tablet would be good if we do that way, because it won't be only verbal but would also help you as like I can write and then you can also see that. So we know that why we are doing this course and what's the learning objective of the course. But now next what we have is like now we have started with stats, we know the different distributions, we know sampling. Now what we don't know is how do we see the interval. So first there are two different estimates. Like last time we saw there were like point estimates and there were interval estimates. So we want to see what's the difference in between those estimates. Okay, Okay, we'll construct and interpret that particular estimate for a single population, both using Z and T transformations, so distribution. So there is one basic difference in between both of them, one where the standard deviation is not known, another where the standard deviation is known. One is used when your sample size is large, another when your sample size is not that large. Okay, then we'll also form some confidence intervals for a given set of population proportion, and we'll see how we should do it for the variance of the population. So first, if we see that, okay, what's the difference, just very basic definition in between an estimate and an estimator. So an estimate is nothing but a specific value of a random variable, whereas an estimator would be something that will give you approximation about the unknown parameter or from your entire population. So that is your estimator. Now, what is the core difference in between a normal estimator as well as your confidence interval? So a single estimator is just a point value, a single number, whereas a confidence interval will give you a range of values. So that is nothing but a lower confidence interval, a upper confidence interval. So why it helps? Okay, I guess that is in for no. Okay, so why it helps in this way is because it will help us add the variability, because our sample population is not only dependent on a single value, but it is dependent on the entire range. So we'll be able to accumulate the errors variability due to everything in there, and not only due to a single population. That is, in that way, would also be considered very biased on a specific value of data. Okay, so how do we differentiate, or how do we have notable definite is like the note points for this particular estimate? So point estimates, if it's for a sample or if it's for a population, how do we write it? So if it's for a population, those are general parameters that you know and have been seeing till now. It's like mu for mean and p for proportion, population proportion. Whereas if it's a sample statistics, I guess in the first or second session, we also had few people who had doubts that, okay, uh, if it's a sample or if it's a population statistic, and there was also one question in such, is like in the quiz, that, okay, which particular, is it a population parameter or is it a sample parameter? So for such cases, you need to know that, okay, if it's a sample, it's just X bar of it, because here we are only dealing with some specific set of values and not the entire population, where mu would be something that is for generally for the entire population. And similarly, for the population proportion for sample, it would be p cap. So that's a small p. Okay. Now, for whenever we do this stats, we always want that there's no bias in our data set. So that means that we are not only relying on a specific value, we want that it to follow the entire distribution. All values should again follow it. So there is a basic definition for it, that this is a variable called, if you all might know till now. So this is something which we called as expectation. So in stats also we have expectation. So someone might also confuse this expectation with respect to average, but no, it's not average. It's like statistically average and taking an average or mean of things. Those are two different values. So over here, it's not average, of course. It's just the expectation. So if the expectation of any sample variable or sample parameter is, if it's equal to the population parameter, then we say that our whatever findings we do have are unbiased. But now, how we can see so? So over here, if you see the first distribution for theta cap 1, another distribution for theta cap 2. So if you see here for the population, for the theta cap 1, the bias, the mean of the, so expectation of the distribution where the mean is lying, it's nothing but at theta. So we say that, okay, the expectation of this theta 1 bar is equals to theta, but it's not equals to theta 2 cap. So hence, in that way, we say that this particular estimator of theta 2 is biased. So we can't consider that anymore, and it's not good practice to also continue. Then we also have certain limits. So then how do you estimate that, okay, how much bias is there? If there's a bias, then how much bias is there? So we have a formula as, we do just the subtraction of this upper formula. So expectation of this cap minus a population variable. If the data set or whatever you're doing is unbiased, then this particular value would be 0 in case of unbiasedness. If it's not, then it would give you some value based on it. Okay. Now there are different estimators for the same. I suppose you might have also gone through the lecture slide. So we also had, if which particular city, if it's theta cap 1 and if it's theta cap 2, then how do we say that which is the efficient estimator? So we compare their variances. Now, someone of you can unmute yourself and can say that, okay, if a distribution has a higher variance, then if is it efficient, or if it has a lower variance, then it's efficient. So how do we say that? So let's say a particular distribution of theta 1, another distribution of theta 2. If the variance of theta 1 is, say, less than that of variance of theta 2, so what do we say? Which particular, so if it's for the sample, okay? So which particular distribution is more efficient over here? So which particular distribution's estimator is more efficient? Any guesses?
Ma'am, please repeat the question.
Yeah. So when we have variance of our population, so here we are considering for the sample that we are looking at, so the sample distribution. So we want to know that if the variance of a particular sample distribution is less than the variance of another distribution, so how do we say that our estimator is an efficient estimator? So if I say, for example, that variance of the first distribution is less than that of the second distribution, then which one of these, theta cap 1 or theta cap 2, is an efficient estimator for my distribution? Well, okay. So we always want in our distribution, there's not more variance, there's not more dispersion. We don't have any much more differences or any more variability. Hence, if the variance of a particular distribution is less than that of the another distribution, we say that this is particularly more efficient estimator for our distribution. Okay. Next set is about the confidence interval. So confidence interval will give you absolutely more information about the entire population. It will give you a characteristic about the population, and it is something that is more than that of the point estimate. So this particular values, it cannot be always 100%. We is like, if you might have seen, there are certain values. So the confidence interval is defined within certain percentage of values. It can be 95, can be 99, can be 96, 98. Those percentage values we give. So how a confidence interval for a particular range is given as 100 times this 1 minus alpha percentage of a confidence level. So that is how you represent that, okay, this is a particular value. Okay. So given all of these, now we not want to know that why, okay, wait. Huh. So then why are we actually doing these things? So how do we estimate it? So first, if a person has a particular sample, he has a mean of the population, but it's also unknown. So mean of the population mu over here, it's unknown. Then he has a random sample whose sample he is knowing that the sample mean he has, X bar he is having. So there itself, he cannot, it's like if he does a point estimate, he would be very relying on the single value that he has, that is of the sample. But now, if he wants to calculate or define the value for the entire population, so how he would do is that he would compute certain, so this is like certain X percentage confidence interval where the mean is lying in between those two values. So that is how your confidence level or confidence interval helps through. So there are different, it's like different intervals for the confidence intervals. You have population mean, proportion, as well as variance. Then mean is also differentiated where your sigma is known or not known. So normal definition for a confidence interval, this definition will lie in every cases, like it's always a lower limit and an upper limit. Now you just want to know that for each of these cases, how it particularly follows. Okay. So it's your point estimate, that is nothing but your sample parameter. This is a reliability factor, that is nothing but your distribution that you would be taking into, and your standard error. Now take into consideration that errors might differ. So the first, if you just say error, that is your standard deviation. If you say standard error, then that is your sigma by root n. Now, if you say margin error, that is nothing but by say some, if we do further, it can be a t distribution or can be z distribution multiplied by your standard error. So these are the three different types of errors that you always have in this kind of distributions. Better if you know the differences in between all of them, and can be a tricky question if need to be asked. Okay. So we'll do a quick example over here. So I suppose all of you know, and I'll just give a quick formula over here. Okay. So if it's a sample statistic and our sigma square is known over here, so the yellow one, our sigma square is known. So the formula for the same is this is our sample or the point estimate minus our reliability factor. And that reliability factor is against the confidence intervals or the probability values at the tails that we are looking at times the standard error. Okay. So this including is the only error. This is the entire standard error. This is the margin error. So taken was like remember this points that okay, which particular error is how, and then we are taking its mean across this particular values. Okay. So this is again this alpha by 2 sigma by root n. Now this is the interval limits that you have. So margin error is clear, error is clear. Now how a particular error can be increased or decreased. So you can see at its standard deviation, about its sample size, and about the confidence interval. So those things are like probably more enhanced in the lecture slides. I won't go through them. So we'll just see some examples. So a sample of 11 circuits. So over here we have the sample size n from a large normal population. So they have told us that the population is normal. So normal distribution it follows has a mean resistance of 2.2. So that is our mu probably. We know from past testing that the population standard deviation is this. So that is our sigma. So what we don't have over here is we don't have the sigma by root n. So you all can quickly calculate what sigma by root n over here would be. This would be something like this. So the value would be there. I don't expect you to give me values over here, but it's just to help you know if you haven't done these things. Now they are asking us determine a confidence interval for 95% confidence interval. So we saw in second and third week again and again that how to look at the Z table. So I guess we haven't looked at the T table yet now because it would be coming now only. But how to look at Z table, we have already looked at. For a particular value, what's the area under the curve or the probability for the specific index? Okay. So for 95% confidence interval, if I have to look for the true mean resistance value, what value would I be looking at? Would be the value at 5%. So that would be like 5% equally split it into two tails. That's like 0.25, or you can also look at 0.05. Okay. So for this particular value, 2 minutes. Huh? Okay, sorry. Okay, over here. So that is our standard error. And then Z value for a 95% confidence interval. I guess till now, if you would be doing this again and again, you, I hope I'm unmuted. If I'm not, yes, I'm unmuted. Okay. So Z value for that 95% confidence interval, that to be that half of the significance level, is nothing but 1.96. So you have this 1.96, and now you know you have the sample statistics parameter. So just you need to compute the difference in between these two values. Right. So this would be your range where your mu lies in. So plus minus would be your half of the ranges. So what is your X bar over here? Is this particular value. What's your Z? You have the Z, you have the standard error, you have over here the standard error. Wait, this is not X bar. What is X bar here? Has them, oh, sorry, this is not X bar, this is your X bar. So for the sample value. So this is not the mu, this is like not for the entire population, but this is only for the sample of 11 circuits. For those only the mu was defined. Okay, because indeed we are wanting to find the true mean resistance confidence interval. Okay, so I hope this kind of examples are clear to you and how to like proceed forward for the same. Next type of statistics are like students t test. So ideally, when should you do students t test is like when you're dealing with the sample statistical parameters, and then when you have the do you know the sigma of the population or not? Is the standard deviation known to you or not? When we do the t distribution, any guesses? Okay. So when we do the students t distribution, we have no information about the population sigma, population standard deviation, but we do know something about the sample statistics. That's why we do this kind of statistics. When so how the sigma for this is defined, it is just a nonetheless. Okay. So when we do this particular statistics, when the sample size is less and we only have the information about the sample and not about the entire population. So this thing also has a similar formula as that of your Z, is nothing but X bar minus mu. Yes, right. And then S by square root of n. So I thought someone had something to say. Okay. Now over here, we also have a concept of degree of freedom. What is degree of freedom is nothing but n minus 1 over here. That means that when the mean of the sample a particular population has been computed, so the number of variables that are free to move around. If they move, then the mean of the population won't differ. So that's a degree of freedom. Now, when you look at this particular student's this T table, the T table has your axis in terms of one would be your degree of freedom, another would be your index value. So those won't be your population. Okay. So So those are like similar assumptions. And then similarly, how we have calculated it over here, if you differentiate this for your mu of the population, for the true mean, your range would be something like x bar plus minus probably. Then your this would be against your degree of freedom, and then you would have this across your tail value, and that would be your sample statistical parameter. So this would be the confidence interval ranges for your true mean value when it's for the t distribution. Okay. This my PC is hanging today a little bit. Okay. So then what we know as of now is, okay, so when your population size increases, so when your sample size increases, what happens is your this t distribution starts to approach your z distribution in a way that it starts to approach the normal distributed data. So we say a standard normal distributed data is your uh, this particular data is t distribution itself, but having a degree of freedom as infinity. Okay, so I hope the difference in between both of them is clear, because you would somehow get this kind of examples in your assignments also and in an exam also, how to compute these particular values. And probably that time you won't have access to Python or MATLAB. That's why you would need to know that how to compute it using the formulas. So the formulas are pretty simple. It's just based on the sample statistics, the population statistics. You need to know when to use what and how to read the Z table and the T table. Okay. So which area under the curve to look at and where. So a simple example similar to the above one. So here we have the sample given. The population mean is given to us. S is nothing but this population standard, sample standard deviation is given to us. And we have to compute the 95% confidence interval for the same. So here you can also use the same formula over here. Same formula. And you can just in the values there. What the values would be is like you have now what you would need to find would be this particular value. Oops, started. Oops. Okay. So what you need to compute over here is you'll need to find this particular value. That would be from the T tables. If you don't know how to read that, I'll show you when the session ends, or perhaps in the next session, as in how we go. Okay. So how do we compute it is you look at the n minus 1. Now you have n equals to 25, you do n equals to 24, and then you look at this alpha by 2. So your confidence interval values. So then you have a table like this, where here you have degree of freedom, here you have the values given for the particular probability where you need to look at, and that will give you a specific t value in your table. So that t value you have to have, and then you input it here. You have the standard deviation, you have square root of n, you have the sample mean. So that is how you input all of them, and you'll get the confidence interval across your true mean. I hope there are no questions over here. If you have, kindly let me know. No, right? Any questions? Okay, I suppose not. Okay. Similarly, there's a course like how we do it for the population proportion. The formula is for the standard deviation. I guess in the last assignment, all of you also saw that for standard deviation, you have like a p cubed by root, and so those also follow similarly for the sample statistics. And their population proportion would also have the similar limit. So those are also within the plus minus limits. Okay. So next question is also somehow within the population proportion kind of thing, where you have a random sample of 100 people. You say that 25 are only left-handed, and then you need to compute the population proportion for the same. So how the true proportion, I guess only the I guess would only be for the sample proportion. So how your population proportion would vary given you have information about the sample of people. So similarly, yes, Gautami, you have something to say? Hope not. Okay. So for that also, what your formula is like is nothing but for your population proportion. Your formula is given by so the random variable now is your population sample proportion minus, now your sample size is higher, so you take the z distribution again. You look at the alpha by 2 levels, and then this is your standard error. So that is nothing but p cap 1 minus p cap, or p minus q, p times q, because 1 minus p is essentially q divided by this. So this is how, so it would be plus minus of this. So the range would vary in between these two values. So Same way, you can look up at the table, find those values, and just input it over here. Now, if you know that, what do you know over here from here, that this thing, are 25 people are left-handed. So how do you compute the probabilities over here? So first would be 25 by 100, another would be 75 by 100. So 1 minus essentially. So this is your P, this is your Q, and those values you can input it over here. Okay. Okay. So then how do you interpret those values? So you get a specific range of values. Now we'll say that it might lie within this or it is in between. We are not so certain. It may or may not contain. We just say that, okay, it is in between. So we are 95% confident that the true percentage value might be in between these two ranges. Although the interval may or may not contain the true proportion, but we know that some value out of the 100 samples will contain the true population values within these ranges that we have. So similarly, how we did for upper thing, for confidence interval also we have different, is like if it's for the mean, for the proportions, population variance, where the sigma is known and not known. So for the same also you have like chi-square distribution. Then you also always like you have similar things following there. So you have the same ranges, plus and minus limits. You just find it through the table. It's like here the crucial thing is you just need to know that how to read a Z table as well as a T table. If you don't know that, yeah, I guess that's a good time for you to learn those things. Probably would also come when you do your maths 4 if you are in bachelor's, or in masters also, or in PhD if some of you are trying to think. So there's a course called as biostatistics. So if, or there's also a course called as statistical modeling. So these are like two courses that are offered in IIT Gandhinagar. So in both of these courses, we are taught this distributions and how to compute for these factors. So these things are good is like if you learn prior to that, those courses. Okay. So then there are different correction factors, then you estimate for the entire population and all. So everything there lies the similar. So what we have seen till now, the normal population, how to create about the confidence intervals, and the it's like similar ranges when your standard deviation is known or not known. Then we have something, okay, I guess that's an extra page. Okay, so we have something called as the null and alternate hypothesis. Okay, so how you develop those? There are again two types of errors there. Their population mean and there's population proportion. Okay, and then we'll just see a basic difference in between both of them. If one can say by unmuting themselves that how do we represent null and alternate hypothesis by, how do we represent these? So null hypothesis is something by H naught. Alternate hypothesis is something by HA. So we say that null hypothesis is something that is challenging us, or that is a tentative, say, assumption about the population parameter, whereas alternate hypothesis is something that we have stated in the null hypothesis is the exact opposite of it. So then there's a very simple thing how you do is that if something is given to you, you just directly assume that what your question asks is true, directly true. So if I'm saying that next day I'll be doing some activity kind of I'll be going to my workspace, will do some part of my thesis or something like that. So my alternative hypothesis is that okay, Jagriti will do these things. Null hypothesis is that she won't do these things. So what is the cost about she won't do these things? So that is how you form this hypothesis. So you see the question, you trick it, you give it directly. But there's also some things that the alternative hypothesis would never contain an equality. So if it is equal to something, if you say now if it's in numbers, if I say that okay, I'll wake up by 7 o'clock, or I'll wake up by before 7 o'clock. If I say I'll wake up before 7 o'clock, my alternative hypothesis would be I'll wake up before 7 o'clock, whereas my null hypothesis would be I'll wake up after or at 7 o'clock. So that it always includes a factor of equality, whereas this one does not include a factor of equality. Okay. Then I guess how to read those null and alternative hypothesis is pretty simple. Now what you have is this null hypothesis are always around the population mean parameter. Okay, so if you have so this H naught, and if this is your I guess let's do it this way. So this is how it was taught to us when it was taught. So you always write null and alternative hypothesis like this, and then you say okay, let's say that my population parameter is greater than that of this particular random sample mean, let's say, that is given to me, and my alternative hypothesis is that no, it is less than that of it. So now we are here assuming that okay, always our alternative hypothesis is the one that is true, that we are saying it at the first. Okay, so here we'll say that this is nothing but lying towards the lower tail also if it's lesser than that of it, right? So it's always lesser than that of it. So it's like a left tailed, or you can also say if you don't want to do left or right, so it's a like lower tail one, or it can also be like one tailed. Okay, now if there is something that is like all direct opposite of it, and this is directly greater than it, so what it would be? Right or upper tail? Of course, it is one tail. Okay. And then if it's like for equal, if it says if it's equal and this says it's not, then it's nothing but two tail. Okay, so this is how your null and alternative hypothesis vary. Now the same thing would be for the difference of means, would be for two sample proportions, would be for a single sample proportion. Everything would follow in line. So this is how you read this null and alternative hypothesis, and you say that how you reject your null hypothesis, or how you accept a null hypothesis. Okay. Apart from hypothesis, there are two types of errors that we have. First is the type 1 error. Next is the type 2 error. So the ones highlighted in pink one here. Now, type 1 error is an error which we say that it's like, what was the term of it? Incorrect rejection, something like that. So what that means is that if your null hypothesis is true, and even though you are rejecting it, so we say that's like incorrect rejection. So your type 1 error is called as incorrect rejection of the true thing that was bound to happen. And if it was a true thing that was bound to happen, we represent it by alpha, that is nothing but population of significance. So your probability that something is of significance, so that is like alpha, and that is like we usually compute it in terms of 95% confidence interval, that nothing but 95% confidence interval. So that is like if you say the population, the statistics to be in between, so that for a two tail would be like within 0.05. So like alpha by 2 would be within those two values. Okay. Next, if you say that if your null hypothesis false, and even though you are accepting it, so that is nothing but your false acceptance. Now, here this false acceptance, the or type 2 error, is represented by a parameter called as beta. And what this beta is nothing but it's normally 20% of your error, or what the values that you compute in. Okay. So these are the two types of error that you have. So normally statisticians, they'll avoid using that to not reject the null hypothesis or accept the null hypothesis. We always say that it is true or it is false. We don't directly say that, okay, we are directly rejecting it. So those are some terms that they follow. There are different approaches for doing this particular finding the hypothesis testing over here. So one way is you do it using a p-value. So that is nothing but your significant value that will tell you whether your distribution or the two particular things that you're looking at are of significantly different or not. Okay, if it's not two, but can be that okay, if your null or this alternative hypothesis is true or not, can be distributed from this parameter. So these are the approaches through which you can see that your hypothesis is true or not. Okay, then you have something called as critical value, and then you have a confidence interval. So if you see if your confidence in the particular mean proportion value is within those confidence interval values or not, then you say that okay, it is lying within it. So we reject the null hypothesis when your p-value for a particular distribution is less than this type 1 error. That was nothing but alpha. So if I say that I'm following 95% confidence interval, so I'll say that okay, it should be less than 0.05. So here I'm only assuming that my distribution is only one side tailed. Okay, it's not two tailed distribution. So I'll say that okay, if the p-value is less than 0.05, then I'll reject my null hypothesis, accept my alternative hypothesis. That is nothing but the research that is truthful to me or that I want. Okay. Yes, someone wants to say something? Okay. Then next you have critical value. So you look at that particular index value where you are having your proportion. Similarly, you'll compute your value against that value. So there are a couple of it's like code chunks in between the slides that how do you compute. So I hope that is like in last session we looked at pretty in brief, we looked at how to compute the CDF, the probability mass function, all those values. So I hope that would be clear to you. If not, then we can compute it today also after the session gets over. Okay. So then it's all about how do we differentiate in between them. Okay. So if we have to do the hypothesis testing, if it's for the p-value approach, how do you do? You'll first develop your null and alternative hypothesis. Okay, better if we write it. So what do you do first? So your first step one is find your null and alternative hypothesis. Right. Your step two is you find the level of significance. It's like whether it's 95% confidence interval, 98, 99, whatsoever is your research that asks, but usually it's like 95% confidence interval. Okay. Then you collect the data, some sample data, through which you'll compute these values. Or either if you have the data with you, then you directly start doing your hypothesis testing. Collect the data and do the test statistics that we did previously. Now here test statistics does not directly mean that do the t test. It's like either the Z or the T, but in case of samples, it will always be T because you don't have much of the data with you. Then if it's a p-value approach, you'll see that if your value is less than the probability significant value, if it's a critical value approach, you'll see if your alpha value is less than that particular critical value, then you'll do the rejection rule. If it's the final one, which was the final one, I guess that was a confidence interval. So you'll see that whether your given true mean value is within the confidence interval or not. If it's not, then you reject. If it's not, sorry. If it's not, then you accept the null hypothesis that okay, it's not. If it's yes or within not or yeah, I guess. Sorry, I said it the other way around. So if it's not there, you accept your alternative hypothesis that okay, it was not there. If it's not, if it's there, then you reject your alternative hypothesis and accept your null hypothesis. Okay. So saying that, we are almost done with the hypothesis testing, I guess. And there were distributions where there are like couple of formulas that you need to consider or need to remember that okay, how do you compute those formulas or how do you find the particular significance of those? So I guess there are some examples and just formulas. So probably from here, all formulas are simply covered. And just what you need to know is that how will you compute and how will you see the Z and T table. For the different approaches, the mean standard deviation, those parameters will come in handy if you know which particular thing you have to apply when. Okay. So I guess if it's done, we can do the assignment thing. Are you all up for the assignment? Or you have any questions? You can ask now, or we can do the assignment, which will help you do your assignment that is due tomorrow, probably. Any questions? Or we can take also a 5 minute break if someone has something to say in between that period. I guess there was one more thing also. So when do we see that your alpha and beta? So there's a true relation between both of them that okay, you see that's okay, we all assume that okay, it's a false acceptance, this is incorrect rejection, one will increase, another will decrease. So based on the sample size also, the sample size increases, the error decreases. If your significant standard deviation increases, error will increase. If your significance value increases, so alpha increases, your beta will decrease. And if it's a true value of the population parameter, then your the power of the population that is beta, it will increase, whereas your alpha will decrease. So how do you compute your power of population over here? So power of population is nothing but it is given by 1 minus beta. So whenever you're writing, say, grant proposal or something, in those cases, you always need to mention the power of the population. Whereas some statisticians will see that, okay, this thing is not given over there, and then this person does not know anything about the stats, they'll directly reject your grant their way around. So you need to mention the statistics everywhere. So why the sample size is this much? While considering, okay, my power of the study is this much, like 80%, hence my beta value comes around this much, hence my sample size is like, say, okay, if you say directly the magical number of say n equals to 30 will directly give that value. But if it's not, then you need to mention that, okay, what particular population is like the power that you're considering, and based on the power, what your sample size comes to be. That was something that was left, I guess. And then, if you don't have any further questions, then we can do the assignment and then I'll leave you all. I guess for the two sample proportions also, it was pretty easy if you know the limits over here. Which ones? This ones or this ones. So everything follows within the same lines. But one thing is different for two the particular distributions, or if there are two sample means that are given to you, everything would be similar. If it's independent, dependent, or population proportion, or variances, or if your sigma is known or not known. So then you know if it's known or not known, you know that which particular distribution you need to follow. But if it's like something based on the variance, so there's a very tricky formula for variance, that variance of a minus b is actually variance of a plus variance of b. If someone knows, they can say why so. If not, let it be a trick. I'll let you know in the next few years, like next session. So following the same, it's like variance of a plus b. So what you do is like sigma square, say if it's the first distribution and next distribution. Following, if there are two distributions, what you have is nothing but a pooled standard deviation that is similar to what you have as weighted mean. So how weighted mean was, if say you have two particular parameters, it would be w1 x1 plus w2 x2 divided by w1 plus w2. So these are like nothing but this is based on your degree of freedom. So similarly for the pooled standard deviation would also be for the entire thing. So following the standard deviation, so this would be -1, this would be s1 square, this would be again n2 minus. So that is your degree of freedom. Okay. S2 square, and that would be n1 minus 1 plus n2 minus 1. So this comes to be n1 plus n2 minus 2. So in this particular, when it's like difference for two samples, your degree of freedom is n1 plus n2 minus 1. Okay, so those things you need to consider over there. I guess based on these, the limits all remain the same. It's just you need to consider the fact, how do you differentiate in between both of them. Apart from it, if you want to compute it using Python, it's pretty simple how we did in previous classes, that compute the CDF at that point. So that would be like at least, at most, you compute the probability mass function. So that would be at that particular value. And you can come with like form some functions for the same. So those are like pretty simple things. It's like simple distributions, and then just import their libraries in it. So if it's not clear, I can also share it in the next class too. So I said something a lot, and I guess no doubts, further doubts. So guess we'll do the previous year questions, and I'll leave you all. Okay. So you can say the answers that you feel. I hope my screen is visible. Yeah, it's. Okay. So null hypothesis, mu1 minus mu2 is equals to 0. So what does it tell us about the distribution? Upper tail, lower tail, two tail, or F test? Now you can speak up so that I'll close the session soon, but we'll also do the previous assignments, and so that you can solve the assignment that is due. Someone saying something?
Two-tail test.
Yeah, yes, it's a two-tail test. Okay. Then we have a sample size of 15 and the population standard deviation is, what will we use?
Z-test for hypothesis testing.
Yes. Okay, so here is something that we need to compute over here, that a quality control manager at the lithium battery factory needs to determine whether the mean life of a large shipment is equal to the specified hours of 375 or not. The process standard deviation is known to be, say, 100, and a random sample of 64 batteries indicate a sample mean life of 350 hours. So state the hypothesis. What hypothesis would it be? Okay, so let's just start from the very basic. What will we do for the null and alternative hypothesis? So what would be our null hypothesis? Someone? So there are like, say, I guess two parts to this question. This can be the A part, and next part is like they are asking us for the mean life of it. So to process report needs to determine whether the mean life is equal to it or not. Okay. So what would be our hypothesis? It's given over there. So we said that, okay, our alternative hypothesis would always be the one that we want directly. But here we saw that equality cannot be in the alternative hypothesis. So it would be definitely in the null hypothesis. So we say that, so this is like, okay, sorry. So this is like your true, or say mean life is equals to this 375 hours, or it's not equals to this 375, right? So this will tell you, so this is your mu naught that is given to you. So these are like our null and alternative hypothesis. Okay. Then what would be the answer to this question?
Is equal to 375.
Sorry? Someone?
Sorry,
I-
continue.
Okay. So mu would be equals to 375. So that is our null hypothesis. Now let's say if you want to know that if our true mean life is lying within that or not, because the question is already asked, but I guess the things are, I guess if it's later. Yeah, it's later. It's over here. Okay. So next in question 4, it asks us that at the confidence interval or the alpha of 0.05 level of significance, is there any evidence that mean life differs from 375? So for that, what will we need to do? We'll have to compute the Z value that we have. Sorry, someone was saying something? Okay. So we'll compute the Z. So that is nothing but this thing divided by sigma by root n. So you all can compute what Z would be. I don't mind if you don't know. Okay. So we also know that for 95% this, what our value is. So that this value should be like pretty much, you should remember it for now, that okay, what the values comes to be around. So when we compute it, I guess for the sample, so if it's or if it's not, so our X bar is for the random sample. So that is this 350, and then a specified value is equals to 375. So this is our X bar. This is 375 is our mu of the population. Standard deviation is given to us is known to be this. So this is our standard deviation. And how many? So okay, I'll just input in the value so that you can compute it later. So your X bar is differs from 375. So this is your 370. Oh, is this? Oh, sorry. Our true mean population is 375. So this would be 350 minus 375 divided by, it would be 100 by, this is your n, so square root of 64. So you'll have your Z value as something as it is a 64.
No, there is not.
What? Okay, then. So your Z values comes to be something. So then what will you do? You'll just compare if your Z value is greater than this particular value or not. If it is, then we'll reject the null hypothesis. If it's not, we say that, okay, there's a difference or not. So accordingly, your question would be there. So result will come. Okay. So next, in Q3, the computed p-value is, so okay, you'll compute the probability from there and you'll know that, okay, what the computed value would be. If you see the Z table, based on that, you'll be able to understand that thing. Okay. In Q3, 95% confidence interval. So this value, if you estimate it, what you will do for this particular question? Can someone say the lower and upper limits over here? We just did it for a couple of times and I also mentioned it over there also. Anyone? No one?
No.
No. Okay. So for the population mean life, how do you compute your proportion values to be? So this can be plus or minus within the z and sigma by root n. So this is how your confidence interval values would be in between, and you just need to compute the values there. Okay. So the mean cost of a hotel is given to you. Random sample of 25 hours resulted in X bar of this. So your sample statistics X bar is given to you. Your sample, this standard deviation Z S is given to you. You have your N over here. So you can compute S by root N. Now you know that for a sample, everything is given to you. So what will you do? You'll compute T. So that would be X bar. X bar you have. This is your mean cost. So X bar minus mu by S by square root of N. Okay. So that way you can compute that, okay, what was the value at, okay. Now, if they haven't said us anything, so let's just assume that it's like 95% confidence interval and you compute this T alpha by 2 accordingly. And you see that, okay, whether this particular value and the value that you compute for the data is greater than or less than it. Okay, so you compute the T statistic for it. Okay. What is the decision on the null hypothesis? So that you'll know. Okay. So in the hypothesis testing procedure, what does alpha refers to? Someone? So is it the confidence level or is it a level of significance? Critical value, it cannot be. 1 minus level of significance, also it cannot be. So which one it is? Like confidence level or level of significance?
Ma'am, level of significance.
Yeah. So it's a level of significance. Remember that confidence level is the level that we computed for an interval when it's in between some two values. So that level is nothing but 100% of, of this 1 minus alpha parameter. Okay, so that is your level, whereas this is the level of significance. If a test leads to the rejection of null hypothesis, then what should have been done? So we are rejecting the null hypothesis. Yes, someone? A type 2 error have been committed or type
Ma'am,
2
a type
mean.
error must have been committed.
Type which one?
A type 1 error must have been
Ah,
committed.
Must. Okay. So we never say that it would be. We'll always say that it is in between or it might be in between. So it may have been committed. Why? Because it says that it leads to rejection of the null hypothesis. Now we know that type 1 error is something that rejects the null hypothesis, but it rejects when if it's true. Now they haven't told us that if it's true or false. So hence we'll say that it may have been committed. Whereas in this we'll directly accept it. So it's like may committed. Okay. So it may have been committed. Yes, that's it for today. If you have any questions, further questions, you can stay in. If you don't have any further questions, you can leave the session. Thanks. Thanks for joining. I'll just save this and upload in the Google Drive that is given to us.
Ma'am, how to do mode function in Python? I mean, like
Which
mean,
function?
median, mode. I have done mean and median, but
Okay.
how to do mode in the Python?
So what is mode function? Sorry, what is mode actually?
Ma'am, the mode is actually categorical data skipping and
No, like the literal definition of mode.
What is the seventh question answer, ma'am?
This one.
No, ma'am. Seventh one.
This is 7th, right? Which one are you saying? Okay, wait. So someone was asking that how to compute mode. So mode is nothing but the maximum occurring value, right? So maximum what would be occur? So how many times something has occurred? So directly
Yes,
you can do mode if you import stats library, or if not, you can compute the frequency of a particular thing that is occurring again and again. Or either for a distribution, if you want to compute mode, then that would be the maximum value that is there in the distribution.
okay, ma'am.
Okay, if someone has any doubts, they can let me know, or else we can close the session.
No.
Okay, thank you. Thanks for joining. Any questions? Well, if there are no further questions, then we can close this session. And yes, you guys also might have some things to do. And we'll meet next week with the next content of week 5 and the assignment questions of week 5. I hope you all will be able to solve your assignments and this thing would be useful to you. Okay. Thank you so much. Thanks for joining.
Thank you, ma'am.
Thank you.